Hello everyone, and welcome to KET Academy YouTube channel. So we are going to be looking at base units, derived units, and dimensions. And some of the objectives of this video is that we are going to understand what homogeneity is and the correctness of a physical quantity, and we're going to know some basic definitions like a base unit, derived units, and dimension. We're going to understand the concepts of dimensional analysis, and we're going to wrap it up with some GC pass questions. It means we're going to provide the solution to some of these GC pass questions. So the first thing we're going to look at, we're going to be looking at some basic definitions, and here we're going to start with a physical quantity. So what's a physical quantity? Before I continue, I will advise that if you're watching this video, it's preferable you get a pen and a jotter and you take down some important notes here that might be of help to you later. So the first thing we're going to look at is a physical quantity, and a physical quantity is any quantity that is measurable and quantifiable. So a unit is a value, quantity, or a magnitude in terms of which other values, quantity, or magnitudes are expressed. So we'll move forward to base unit, and a base unit is simply a quantity whose measurement do not depend on other physical quantity and are used to define all other physical quantities. So an example of a base unit, right, or of a base physical quantity is length, time, mass, electric current, amount of a substance, temperature, luminous intensity. We know that there are actually 7 of these base units, and it is a requirement to know them and their symbols with like the units and their symbols. So the first here is like a picture of all the 7 base units with their names and the symbols. So it's very important to know these units. The next thing we're going to look at is the derived units. Derived units are simply quantity whose measurement depends on the measurement of base units. So example of some of these derived units are volume, velocity, density, work, force. So I'm going to take a moment to illustrate how derived units actually depend on the base units. So to get ahead, we know that volume can be calculated as the area times let's say the length, or area times weight, or length times length times length. So we know that the area is also like length times width, and this can also be measured as length times width times height. So these are all, a volume is made up of the base unit of length, right? Therefore the unit of volume is actually meters cube, and this meters cube actually comes from the base unit of length, which is meters here, and meters here. So multiplying these 3 gives us meters cube. So basically volume is a derived unit because it actually comes from the base unit of length. So the same thing with velocity. Velocity can be calculated as the distance all over the time. We know distance also is the length, and the time is, or these two are base quantities, and we know length is measured in meters. So when we are talking about the unit, you always make sure you write their unit, and the unit of time is second. So the unit of time here, is second. So when talking about this unit, we should always make sure to write it. So to do this properly, you know that velocity is actually distance all over time. So the unit of velocity will simply be equal to the unit of distance, or the unit of length, because this can also be represented as length, all over the unit of time. So after writing this, and then you write the unit of distance is meters and the unit of time is seconds. So we can write this as meters per second, or better still meters/seconds. So we see that velocity is actually derived from the base unit of distance and time, which are all base units. So the same thing will go for density, which is the mass per unit volume, and we already saw that volume is a derived unit and the mass is actually a base unit. So it goes on and on for work, for force, and all of that. So I'm going to keep I think I'm going to leave this as an exercise for you to do. You're going to do this and put your results in the comment section. So your exercise will be to come up with the units of density, work, and force. You put that in like in the comment section. I'm going to check that out and if possible give you a reply. Now here is a list, so I'll advise you all to jot some of these points here. We see that here are a list of derived quantities, and like the GC cannot go above this. So if you're able to master this, know that no question will come that is going to disturb you at your GCE. So the first one is displacement, and the symbol is the name is meter, so the symbol here will be M. The second one is area, and area is measured in meters squared, and the symbol is M squared, and so on and so forth. So in the course of our video, we're going to actually use all of these quantities to solve. So it's very important to take note of this, so that when we're solving and applying all of this, you'll be able to follow up. So now we're going to look at dimensions, and here a dimension actually indicates how a given physical quantity is related to the base quantities through its defining equations. So we're going to go back to the base unit. We realize that, or we saw earlier, that there are 7 base units, and these base units, they have their dimensions, and the base unit or the dimensions of length is simply L. So it's also very important for you to know all of these units, because you might be asked to work with dimensions instead of units or base units. So it's very important to know this, and make sure that when you want to write state a dimension, always put it in squared bracket, meaning that if I want to write the dimensions of length, I will definitely write it like this: of length should be equal to L. And remember, to write the units of a quantity, we write unit of t is equal to second. If you do not write this statement or put it in a curly bracket, it's going to definitely be wrong, because we are used to with formulas like, let's say, velocity is distance over time. Here you can simply state this and you'll be recognized by everyone, but if you just state this, no one will actually know this. That's why it's always important to specify that you're dealing with units. Now moving forward, here are a list of some derived quantities, their dimensions. So as we earlier saw derived units, we also have derived dimensions, and it boils down to always breaking it. Now I'm going to take an example for me to illustrate how to derive or to get the derived dimension. Now let's take let's say force. We know that from the formula, force is mass times acceleration, right? And we want to deal with the dimensions here. So we have to put the dimensions of F will be equal to the dimensions of MA. So we can further simplify this as stating this is the dimension of A, or rather the dimension, well, it's still the same, and the dimensions of M. So just to write this, we have that. Now the dimensions of mass, as we all know, is capital M. So we're going to write this as a capital M. Now we know that acceleration is actually the rate of change of velocity, and is measured in meters per second squared. So the meters here is represented by the base unit of length, and we know the dimensions of length is capital L. And the seconds here, which is the time, the dimensions of seconds or the time is actually capital T. So we're going to write a capital T and put our -2. So we have to know how to come up with this. which boils down to what we have on our slide or on our picture. So we're going to look at dimensional analysis, and basically this is a mathematical procedure that makes use of dimensional homogeneity to find the relationship between quantities and to check the correctness of an equation or to determine the unit of variables in an equation. So that is what basically dimensional analysis is, and it's like the basic idea of what we're actually doing in this video. So we're going to move forward to some of the limitations of dimensional analysis. Remember that the first part we're going to talk of is the presence of dimensionless constants. You know that this dimensionless constant cannot be verified in an equation, and from here we can come up with a hypothesis stating that an equation or a physical quantity can actually be homogeneous but not correct. So if we are to illustrate this, we'll take an example. If we have an equation, let's say f equals to ma, and we have another equation f equals to 2ma. These two these two equations are actually homogeneous, but one is wrong. Now the one that is wrong, we cannot actually verify if it is wrong or not, because there is a presence of a unitless dimensionless constant, which is these two, and by experiment there is no 2 in the formula. Therefore the second one is definitely wrong. So if we were to test for the homogeneity, we are going to say it's homogeneous, but we cannot verify if it is correct or not. So that is something we need to really take care of. The second reason or limitation that we're going to look at is the existence of additive terms. Now when we talk of additive terms, we might talk of a quantity. Let's say if we have a formula v equals to u plus 80. For us to know the units of, or for this equation to be homogeneous, the additive terms on both sides of the equation must all be equal, meaning that the unit of v, velocity, should be equal to the unit of u, and all of that should be equal to the unit of 80. So if in an equation we write this and we write another equation v equals to 80, definitely the first one is correct, but the second one is wrong because we have omitted an additive term here, u, but this equation is homogeneous. So those are some of the limitations that dimensional analysis actually propose or brings forth. So the third limitation we're going to look at is quantities having the same dimensions are not necessarily comparable. So in this case, we are talking of torque and work. These quantities, the units of torque are basically the same as the units of work, but these two quantities are not equal. So this already is a limitation. They are not physically equal. And the last point that we're going to look at is quantity containing logarithmic and trigonometric functions cannot be checked, because logarithmic and trigonometric functions are basically unitless, so we cannot verify if they are present or they are absent, or if their presence would make an equation correct or homogeneous. So those are some of the limitations of dimensional analysis. Now we're going to solve some examples. It says that given the equation below, what are the units of G? So I've been given an equation. This is a force existing between two masses, a gravitational force existing between two masses. So if we were to look for the unit of G, the first thing we need to look for is we have to make G, express G as in terms of the other variables. So the first thing we need to do is to make G subject formula, and to do that we have F equals to G m1 m2 all over r squared. Now we have that. The first thing we need to do is to divide all through by 1 and cross multiply. If we cross multiply, we're going to have F times r squared to be equal to G m1 m2. Now since we're looking for G, we're going to divide all through by m1 m2. So this is m1 m2 here, m1 m2. So this alone would imply that g will simply be equal to f r squared all over m1 m2. Now to look for the units of g, we have to write the statement that the unit of g will be equal to the unit of f r squared divided by the unit of m1 m2. Now if you do not put this statement, everything is going to be wrong. So after stating this, we are simply going to go directly and put in our unit. We know that f can be represented as ma, and m is measured in kilogram, which is the mass, and acceleration is measured in meters per second squared. Now r is the distance between our two masses, and we know distance is measured in meters, so it will actually be meters squared since r is squared. So it will be meters squared divided by m is the mass, and m1 and m2 are the masses. So since they have the same unit, it's actually going to be kilograms squared. So what is left for us to do now is just to simplify this, and simplifying that, we're going to have kilograms per kilograms. Now how did I get this? From laws of indices. Dividing two indices of the same base, we actually subtract the power. So we have 1 minus 2 here will give us minus 1. Now mass here is raised to the power 1 and mass is raised to the power 2. It boils down to the law of indices, which states that multiplying two indices of the same base, we simply add the power. So it will be meters per cube here and per second squared. So basically these are the units of our constant g, the gravitational constant. Question 2 says the pressure P on a gas at a volume V and absolute temperature T are related according to the gas equation P plus A all over V squared times V minus B equals to CT, where A, B, and C are constants. 1. Explain how you will test the correctness of a physical equation. B. Can a physical equation be both measurable and dimensionless? Determine the units of A, B, and C. So this is an interesting question. The first part says that we should explain how we are going to test for the correctness of a physical equation. We know that for a physical quantity or an equation to be correct, it needs to be homogeneous and should contain unitless constant, the correct unitless constant on both sides. So when looking for the homogeneity, we can either use dimensions or base units to check if it is homogeneous, meaning that the additive terms on both sides should be equal. So if you're able to prove that it is homogeneous and contains the correct unitless values, constants, then it is correct. The second part says that can a physical equation be both measurable and dimensionless? Here the answer is simply yes. The answer is simply yes, because we have quantities like the refractive index, angles. These are quantities that are measurable, but there are unitless or dimensionless. So definitely it's yes. And the third part, or the third question, says that determine the units of A, B, and C. So here is actually where we are going to test our knowledge on units. So we have been given this quantity, and we know that for a quantity we can only add quantities or quantities that are similar, meaning that if we have two terms and we are adding them, definitely those two terms contain the same unit. So what am I trying to say here? In the equation above, P plus A all over V squared times V minus B equals to CT. Now in this equation, if we state that the unit of V should be equal to the unit of B, because basically V minus B can be written as V plus minus B, meaning that they are still additive terms. Since minus is a unitless constant, we can actually put there minus 1. Then the unit is not going to affect B. So if we want to look for the units of B, we are simply going to look for the units of V. And the equation stated that V is actually the volume, right? So the units of V will simply be meters cubed. So that's our answer for the units of B. Now to get the units of A, we know that A divided by V squared is added to P, and we know V there was volume, right? Yeah, so we're going to state here also that a unit of P should be equal to a unit of A all over V squared. So that's what we're interested at. So to get a unit of A, the unit of A will simply be, so the unit of A will simply be equal to the unit of P times the unit of V squared. And we're told in our equation that P, where P is the pressure. So we know that pressure is the force per unit perpendicular area, meaning that the pressure here can be written as force all over area, and the volume here can be written as V squared. Now, the unit of force is kilogram meters per second squared. We saw that earlier. We know that V here is a volume, which is meters. Volume is measured in meters cube. Now, squaring that is going to give us meters to the power 6. Now, divided by the area, which is meters squared. So, doing that, we are going to get the unit of A to be, we'll simply simplify that, which will be kilogram meters. If we subtract that, we're going to have 7 minus 2 kilogram meters to the power 5 per second squared. So basically that's the unit of A. So that is a unit of A. Now, to get a unit of C, there's something interesting we're going to do. Good. Now, to get a unit of C, we have to actually expand the left hand side. Now, why are we doing that? Because we cannot directly state that the unit of CT is equal to the unit of V minus B, or the unit of CT should be equal to the unit of P plus A over V squared. So we have to have terms that are actually separated, or that we can actually equate. So to expand that function, we're going to have PV times PB times plus A all over V minus AB all over V squared equals to CT. So when we expand, that is what we're going to have. So from here, we're going to look for the simplest term in order to create a unit. So we're going to state here that the unit of PV should be equal to the unit of CT. And to get a unit of C, we simply have, so the unit of C will simply be the unit of PV all over T. So we know that T was the absolute temperature, and temperature can be measured in kelvins or degrees Celsius, and we know pressure is force all over area. So we're going to write this as force all over area times the volume divided by we're going to consider Kelvin in this case. So to get a unit, the final unit will simply be kilogram meters per second squared times meters cube per Kelvin. Now we can further simplify this as kilogram meters to the power 4 per second squared per Kelvin. So that will be the solution for this question. We're going to not finalize. So the first thing we need to do here is, for this equation to be correct, it should be homogeneous, meaning that the units of S should be equal to the units of UT, should be equal to the units of they have AT squared, and this equation should also contain the correct unitless quantities or constants, because if we look at this, we can write this as S equals to UT plus AT squared. Now this equation is going to be homogeneous, but it's going to be physically wrong because it does not contain the correct constant, unitless constant, which is a half. So basically that's what was required of us from this question. So the last one is the fourth one says that what are the units of the intensity, given that intensity is P all over A. So I'm still going to leave this as an exercise. I'm expecting you to solve this and put your solutions in the comment section. I'm going to check that out. So we are going to conclude by answering this GC equation. So this is GC 2015 question 1, and it says that what is the homogeneity of an equation? So as we rightly said earlier, a homogeneous equation is an equation whose the units of additive terms are equal on both sides. And here we've been given an equation. They say the equation is P plus Hg times rho plus rho v square equals to K. They say this equation is homogeneous, where P is the pressure, H is the depth, G is the acceleration due to gravity, and V is the velocity, and K definitely is a constant. They said determine the base units of K. So there are various ways in which we can go about this. The first thing we can say here is that we can state directly that the unit of K is equal to the unit of P, which is the pressure. Or we go directly by stating that the unit of K is equal to the unit of Hg rho, or the unit of K is equal to the unit of rho v squared. In each of these cases, it's going to give you the same answer. So to get or to go to the shortest or the shortest possible answer, we're going to say the unit of K should be equal to the unit of P. So since P is pressure, we're simply going to say this is the same as the unit of force on area. And what do we know? Force is kilogram meters per second squared. I guess by now we must have known that the unit of force is that, and the unit of area is meters squared. So we have to simplify this. Simplify now, we're going to have kilogram per meters per second squared. So basically that's the unit of K. So that was what was required from you to get 6 marks straightforward. So basically that is it for this video. Thank you all for watching, and see you guys in the next video. So make sure to share this video with your mates. If you need any topic in physics, maths, chemistry, additional maths, further maths, just indicate in the comment section so that we can prepare notes on that and we'll share with you through our YouTube channel. We're also going to be sharing the PDF of this video, or the PDF notes of this video. So if you're interested in getting it, you have to put in your comment section your number indicating your interest, so that we can link you up to one of our WhatsApp groups, and from there you'll be able to receive directly the PDF of this. So wish you all the best and see you on the next video.